about ablative materials, and in particular, we will continue speaking about how we can characterize an ablative material. Okay, during the last lesson, we saw together the application of ablative materials and also some method of characterization. Now, we start looking at these important points. Properties to be evaluated for an ablative material. Okay, we have to consider that we have to know all the decomposition kinetics parameters. This is very important, and during this lesson we will go in depth for this point. Then, char and virgin specific heat. We know that ablative materials are semi-active in insulating materials, not insulating, thermal protection system, okay, insulating materials. And as long as we have to deal with thermal problems, we have also to characterize the thermal properties of this material. And so we need to evaluate the specific heat of the virgin state of the material, so the material without pyrolysis, and also the specific heat of the charred state of the material when the pyrolysis had happened. Then we have to understand also what is the char and virgin porosity and permeability. Why these parameters are so important? Because we have to understand that the pyrolysis happen inside the material. There is a layer, there is the outer layer with charge. Then there is an inner layer in which the pyrolysis takes place. And in this layer, we have the formation of gas. This gas has to flow through the porous material. So we have to understand also how this happens. And for this reason, we have to know porosity and permeability of our materials. Then, char and virgin thermal diffusivity, conductivity and emissivity. Okay, why? Because we have an exchange of heat with conduction with the external fluid layer, but we have also radiative phenomena. Okay, so a radiation which warm up the material, also a ray radiation. And for this reason, it is very important to know the value of the emissivity of our material. Then, enthalpy, composition and viscosity of pyrolysis gases. Also, these properties are very, very important because thanks to these properties, we can understand also the velocity of the recession of our material. Okay, this is important also to understand the impact of the blowing effect on our material. If you remember the blockage effect, it's caused by the gas who flow through the boundary layer, and in this way they can hinder the convective exchange with the outer part of the material, in which we have a flux at high temperature, also at 3000 degrees. Okay, so all these parameters are very important to understand the behavior of an ablative material, and they are very important also to have the possibility to build a finite element model for an ablative material. But during this lesson, in particular, we will speak about the decomposition kinetics parameters. During the last lesson, we started to observe this important equation, chemical equation, in which we can consider the resin, the phenolic resin, if we consider a carbon phenolic ablator as the only reagent, and two different kinds of products, the pyrolysis gases and char, which is solid. In particular, we defined also the conversion extent. This parameter is very important because it is very easy to manage this parameter, because alpha is equal to 0 at the beginning of the reaction, and it is equal to 1 at the end of the reaction. In fact, what does it mean? This W is the weight of our material. We know that we will have an initial weight of our material and a final weight. The difference of this weight is because we have a decomposition reaction of pyrolysis. So we will have also some intermediate values of this parameter, because during the reaction we will have a different weight of our material. Okay, so if we substitute in Wt the value of W0, we will have 0, alpha equal to 0, and if we substitute to this value Wf, W final, we will have 1. Okay, so this equation is very important because it allows to us to understand how will change the value of alpha during the decomposition process. Okay, so we can consider that the variation of alpha during the time or according to temperature, and during these lessons we will understand that it's the same thing to speak about time or temperature. Okay, depends on two different functions. The first function, K, depends on temperature, and the second function, F, depends on the extent of conversion. These two different functions can be defined in different ways, but the first one, the function of temperature, can be written according to Arrhenius law. Arrhenius law is a very famous law, a chemical law, which allows us to define the velocity of a reaction, and it depends on three different parameters: the pre-exponential factor, the activation energy, and R, which is the universal constant of perfect air. Okay, so two parameters. Okay, in particular, the activation energy is the parameter who let us understand that we need a certain amount of energy to allow the activation of a reaction. And A is another important parameter, which is if A is higher, then the velocity of the reaction is higher. Okay. Then we have another function. We have this function F, which is a function of alpha, the extent of reaction. This function could be of different kind, okay? And in particular, there are three different shapes of alpha, for which we have to choose a different value of F. In particular, we can have an accelerating kind of reaction. What does it mean? That the reaction began at a low velocity, and then this velocity began higher when it is at the end. Then we have a decelerating type of reaction. This is this one, 2, in which we have a high velocity of the reaction and then the velocity lowered, or a sigmoidal model, which is the number 3. Okay, so we have a reaction with a low velocity at the beginning, then there is an increment of the velocity, and then another decrease of the velocity of reaction. So I can say that there are a lot of function f which can be chosen for this kind of application, but according the scientific community, these 3 different kind of function are the most employed for this kind of application.
Excuse me, Professor.
Yes.
We should choose one of them, or based on our reaction, we choose one of them. I mean, when we want to find the d alpha over dt, so we should have this f alpha of t. How we should understand which one is proper for our reaction?
Okay, we can choose the right equation according to experimental values. Okay, because during the lesson we will see that there are some experimental evaluation that we can use in order to understand the trend of alpha. So according to some experimental analysis, we can understand how is the best way to express the expression for alpha, f of alpha. Okay.
Okay, thank you.
Okay. Then, so we can choose this function, okay, according to some experimental analysis. And then we can have our function in this form. Okay, so the Arrhenius equation for the function k, okay, and this function. I choose this kind of function because for this is the typical function used for phenolic resin. Because for phenolic resins we have this kind of shape. Obviously, in this case, in this schema, we have 3 different curves which are very different one from another, because this is a graph used to let you understand more or less the shape, okay? But if you calculate these curves experimentally, obviously it is not so easy to choose what curves you have to use, okay? But in this case, we have a lot of literature data for phenolic resin, and so for this kind of material, we can say that we can use this equation here, okay? So now we have this function for the derivative of alpha to time. Then, if I look at this equation, I have 3 different parameters which have to be calculated. A, the pre-exponential factor, the HA, the activation energy, and then N, which is the order of reaction. In order to calculate these parameters, we can use a method which is called thermogravimetric analysis. Okay, thermogravimetric analysis allow us to obtain some data with which we can calculate, for example, the activation energy. I don't know if you studied thermogravimetric analysis in other courses or during this course, but I will repeat to you the basics of thermogravimetric analysis, which is a concept very simple. In fact, when we have to perform a thermogravimetric analysis, we have a furnace in which we can put a sample of some kind of material. We can warm this material at a certain temperature or at a constant heating rate, for example. And during the heating, we can evaluate the weight of our sample. Okay, and this procedure can be carried out also in a controlled atmosphere. Okay, so in vacuum or in inert gas or in an oxidizing atmosphere. Okay, so this technique can be used for a lot of application. Okay, so we have a sample inside a furnace. We have a controlled heating of this sample, and we can evaluate the weight of the sample during the heating. For example, this procedure could be used also for study the formation of some oxide on metals, for example. The kinetic of the oxidation. It is very common. But for our material, we can use this strategy in order to have some data useful for the evaluation of the activation energy. Okay. In this slide, you can observe the thermogravimetric curve of a material. Okay, so this is the weight percentage of our material, which is obviously 100% at the beginning. Then there is the heating without oxygen, because we know that pyrolysis is a decomposition process which happens without oxygen. And then we have a certain loss of weight, and then a final plateau. Okay, so from this graph, at the first glance, we can understand that the reaction of pyrolysis can start at about 300 degrees. In here, there is a small loss of weight in this first part, but this loss of weight is very small, and for the first part of this graph, the loss of weight can be also the loss of some water inside absorbed inside the material. Okay, so it's not considered. But after 300 degrees, the loss of weight is important. Okay, and then we have this plateau. So we can understand that at this point, the reaction of pyrolysis is ended. Okay, and this is important. In here, you can observe a DTG curve, derivative thermogravimetric curve. This is the derivative of the first one. Okay. This curve is very important because let us to understand better what happened. In fact, in here we can observe only the variation of weight, but in here we have different peaks. These different peaks means that there is some different points in here, okay, in which we have a variation. And this variation could be observed very well with the derivative curve, okay? And it is very meaningful because this variation means that I do not have a single reaction. Okay, the pyrolysis reaction of a phenolic resin is not a reaction who happen in a single step, but we have at last 2 or 3 steps of reaction. And this will be very, very important, because this means that the 3 parameters that you look at here cannot be evaluated once, but they have to be evaluated for each step of reaction. Okay. This is the new form of our equation when we have a multi-step reaction. Okay, we have to evaluate not these parameters for all the curve, but for the different step of reaction. I know that for now it could be not so clear, but during the lesson we will understand more in depth this concept. Okay, the activation energy. During this lesson, I want to show you how to use thermogravimetric curves, some thermogravimetric curves for obtain the activation energy for ablative material. Okay, there are different models which could be applied to these curves, and which allow us for obtaining the activation energy, which is one of the most important parameters for the reaction of pyrolysis. Okay, I will try to use my okay, this one. Okay. Well, when I have, sorry if the graphic is not of high quality, we saw that we have a thermogravimetric curve like this. Okay, this could be the temperature or time, because usually we have a parameter beta, which is the derivative of temperature on time, which is a constant. Okay, so we can study the weight percentage or alpha, it's the same, depending on temperature. Okay, so you have to imagine that I have a little sample of my material, which is generally reduced to powder, grinded powder material, also on the phenolic resin, because it's the phenolic resin which has the pyrolysis reaction. This material, I warm up this material with a constant heating rate. Okay, I have a constant heating rate, and during the heating I evaluate the weight of my material. Okay, if I choose another heating rate, a faster heating rate, I will have a curve very similar to this one. Maybe. Okay. No. Okay. But with this different shape. And if I perform this analysis with another heating aid higher than the other two, I will obtain another curve of this shape, and so on. Okay? Okay, so I have these curves with different heating rates. And okay. And I can have also the derivative curves, okay? As I saw before. I can have also, sorry, no. Okay, okay. I cannot cut. Okay. Again. Okay. The derivative curves can have this shape. For example, okay, continuous line, not like this. Okay, so this one will be in this way or in this way. I can use alpha or W at the same time. It's not difficult. They differ only for a constant. Okay, I hope this is clear for everyone. And obviously, if I have three different heating rates, I will have also three different curves as the DTG. Okay, so I will have this one, then this one, and then another one like this. Okay, so a different heating rays cause a little shift of these curves. This is the first part. This is a very important point. It seems simple, I think, but it is very important. If we go to this equation, okay, in here you have three different names: Ozawa, Friedman, and Kissinger. These three names correspond to three different methods used to evaluate the activation energy, and they depends on the strategy used on this equation. Okay, so during this lesson we will understand only how to use the Friedman method, because the Friedman method is the simplest. It is very common, very used. It is quite reliable, even if nowadays there are some thermochemical software which use modern method. Okay, but in this case I think that this method could be understood very easily, and it is also very interesting. Okay, so we have to remember this equation, and in order to understand the Friedman method, okay, we have to do this. We have the equation in this form. Okay, I hope to write better, sorry. equal to the exponential factor on RT, this temperature, multiplied for the function f. Previously, we saw that we used to write the function f as 1 minus alpha elevated at n. But in this case, Friedman is a model-free. Okay, it's a model-free method. This means that it doesn't matter what kind of function f we can use, but with this method we can evaluate the activation energy also if the function f is not defined. Okay, and so for this reason in here I will write this one and not more. Okay, we can write this natural logarithm of equal to a, oh sorry, okay, logarithm, natural logarithm of a. In this case, if I apply the natural logarithm to this one, I have this plus, okay, I have this equation. In this equation, I can consider this one epsilon, this one as q, the epsilon intercept, okay? I can consider this one as m, the angular coefficient, and this is my x, not t bar, x equal 1 on t. Okay, I have a straight line. I have the quotient of a straight line. Okay, so if I can, no. Okay, so I can use the equation of this straight line with my derivative curves of the thermogravimetric analysis. Okay, I will erase, yeah, sorry, in this way because just an observation. I wrote this. Here t is time, okay? But I obviously can consider it also that if I perform a thermogravimetric analysis with a constant heating rate, beta, I can write beta as the derivative of temperature on time, okay? So I can write this. Okay? And this term in here is beta, which is the heating rate for me. It is the constant heating rate at which I performed the thermogravimetric analysis of my sample. Okay? So we have this equation. I write the equation in this way because it's simpler. Plus, okay. I have this equation, and this is my x-axis, 1 on t. I have the y-axis, okay? And I have all the points that I want because I performed the thermogravimetric analysis. From the derivative of the thermogravimetric analysis, I have this value, the alpha on the t. I know that I have also a constant heating rate, beta, and this value corresponding to a certain value of temperature. So I have points. And I can have different points for different values also of the heating rate. Okay? I can have these values. Thanks to these values, I can have a straight line. The angular coefficient of this straight line is this value in here. And so, thanks to this to the evaluation of the angular coefficient, which is very simple, obviously, I can have also the value of the activation energy because R is the universal gas constant, so it's value that we know. So I can calculate the value of the activation energy. This is a very simple method. You can observe that we only have applied the natural logarithm to the equation. We do not have to decide the equation for the function f. Okay, so this is a model-free method, and it is really very simple. Okay, we can have how much points we want according to how much different heating rate we used for the thermogravimetric analysis. So in order to apply this method, it is very important to have several points. In this case, my example is only with 3 points, but obviously more points we obtained, so more different heating rates we choose for this application, and better will be the quality of our estimation of the activation energy. Obviously, in this case, this method is very simple and we can have an analytical approach, okay? But there are also some thermochemical software who used also the Friedman method, but also other methods which are able to have also more accurate evaluation of these important parameters. In here, we have also Ozawa and Kissinger method, which are different because they can be applied in different way. For example, the Ozawa method, it's very good, but only for certain condition. Okay, and also for Kissinger, we can have good evaluation. It is based on another concept, which is based on the temperature at which we have peaks in the derivative thermogravimetric curve. Okay. But they all are very simple method. Then, once I have obtained this parameter, the activation energy, I have two other parameters which have to be evaluated. And for this purpose, I can have use different tools. For example, here I use a tool of MATLAB, not a very easy tool, in which and not only my MATLAB tool, but I use also this function in here. What does it mean? When I have this function, okay, I have f with alpha, which is in this form, okay, and if I have to rebuild the, sorry, we have to consider this. When I have to deal with this thermochemical model, I have this equation with which I can rebuild the thermogravimetric curves. Okay, so what I do, it is a method with which I can rebuild these curves. Now, according to the scientific community, we have two different approaches. An approach in which we have to rebuild the curve according to the chemical phenomena which occurs. Okay, in fact, if we speak about phenolic resins, everyone says that we have three steps of reaction. Okay, and in fact, if you perform a thermogravimetric analysis for these materials, you always found a DTG curve like this, in which you have 1, 2 peak, and in here you have another peak which is covered by the second one. Okay, but there is a chemical model for these three different steps of reaction, and so in the DTG curve you will find three different peaks. There is another approach. Another approach say, okay, I only need a model with some parameters which allow for the rebuilding of the thermogravimetric curves. It is what I need. Okay. Obviously, this second approach is a very practical approach, is a mathematical approach. The writing of this equation is more chemical approach. Okay, and it is a very typical, very typical approach for the evaluation of the thermochemical parameters of the phenolic, the pyrolysis of the phenolic resin, for example. Okay. Only one more thing about this, and then we will speak about something else, only always on ablative materials, but we have to consider that when we have a DTG curve like this, we have three different peaks. These three different peaks are characterized by three different groups of thermochemical parameters. Okay, this means that I have a value of activation energy for each peak, a value of pre-exponential factor for each peak, and a value of the order of reaction for each peak. But if my experimental curve is this one, how can I do? Okay, so my graphic abilities are not so good, but we will try to understand together what we can do when we have a multi-step reaction, and generally not only for the pyrolysis of phenolic resin, but we always have multi-step reaction. It's very difficult that we have a single step reaction. Okay, so I have this DTG curve. This is a very typical shape for phenolic resin. Okay, how can I do? I can separate the peak. How? With a Gaussian curve. Okay, I can use, for example, a mathematical software which is able to individuate the peak, and it is able to substitute the peak with a Gaussian curve. And, for example, one Gaussian curve, two, and three Gaussian curve. I have to rebuild the derivative thermogravimetric curve with the sum of three different Gaussian curves, which has the point of the peak which correspond to the peak in the DTG curve. Okay, obviously this is very important. Then I can integrate each derivative curve, which is a cumulative curve, and if I have, this is a, sorry. Okay. This is a Gaussian curve, sorry for the graphic. The integral of this curve is something like this, okay? And this one is very similar to a TG. This is the trend for alpha, okay? So it's a sort of contrary of the DTG. It is 0 at the beginning and 1 at the end, okay? And so on. So if I have a multi-step reaction, I can individuate the number of steps of reaction according to the number of the peak in the DTG curves. In this case, I have to calculate the thermokinetical parameter for each peak. One peak can be approximated with a Gaussian curve. All the Gaussian curves used as to be optimized to rebuild the DTG curves, the original DTG curves. Okay. Once I have all the Gaussian curves, I can apply the method that we saw together, for example, the Friedman method, in order to obtain the activation energy. And then I can apply also some mathematical tool in order to obtain also the pre-exponential factor and the order of reaction if I need. Okay, these parameters are very important in order to have all the necessary parameters for the modelization of an ablative material. But not only for this reason. These parameters are very important also because they describe the behavior of an ablative material. For example, the variation of the activation energy could be an important parameter to evaluate. Higher is the activation energy of a material, higher is the energy that I have to employ for the decomposition of my material. And so this could be, for example, very important because I know that the energy absorbed by the material during the decomposition is one of the mechanisms who allow for an absorption of energy. Okay, so it is a very important, these parameters are very important to describe the behavior of an ablative material. Okay, then this is, for example, what we can obtain with a finite element model. Once I have all the parameters needed, I can use some commercial finite element program, software, in order to rebuild the behavior of an ablative material. Generally, these tools are very important because we saw together that in the ground facilities, it's very difficult to reproduce at the same time all the phenomena occurring during a real re-entry of a vehicle in atmosphere. Okay, because we cannot reproduce the velocity and at the same time the enthalpic condition of the fluid, for example. And so some finite element models can be useful to combine all the important parameters. In this case, you can observe simply the rebuild of a test in a plasma wind tunnel facility of a sample manufactured by our research team. And in here you can observe that thanks to the finite element software, we were able to estimate the surface recession of the material, the density variation, which is very important to understand the deepness of the pyrolysis layer, and also the temperature distribution inside the sample. Obviously, we used all the information of a plasma wind tunnel test in order to rebuild this behavior. Okay, but once I have a reliable model, I can do something very important. I can vary, I can modify some parameters. Obviously, the modification has to be very very small. I cannot change too much the density of the material. It is not it is not possible. I can have some results which are not reliable, okay? But I can do something small variation in the characteristics of my material, and I can understand, thanks to the simulation, what can change in my material. Obviously, I have to do this very carefully because, for example, I can say, okay, I change the density of my material. At the origin, the virgin density of my material is 300 kilograms on square meter. I change 320, but in that case, I have also to change the density of the charred material. And the conductivity, yes, I have to change also the conductivity of my material, because obviously if I have, for example, more resin inside my composite material, then the conductivity will change. Okay, so I can modify some parameters in a small percentage, and I can understand something, but I have also to remember that it is not possible to change all my model, to change in great percentage some parameter of my model and consider the model still reliable. Okay, so I can use it in order to understand what could happen, but I have to remember that all the parameters are connected one to another, and so it could be not so easy. But for example, I can understand what happens if I change the thickness of my material. Okay, what happens if my material is thicker or not, and so on. Okay, so there are some parameters with which I can work more. I can do more. Okay, I can change more, and the model could remain reliable. Okay, this is only an example, obviously. But now, during the last part of this lesson, we will see together some example of experiments in a plasma wind tunnel facility, which were carried out by our research team. In particular, in this case, you can observe an ablative material composed by a carbon felt and phenolic resin, okay, with a density of 500 kilograms on a cubic meter, okay, and this material was tested in Scirocco. Scirocco is the plasma wind tunnel facility of CIRA, the Italian Center of Aerospatial Research, and it was tested some years ago in 2009, and it was the first success of our research team, because it was built up with a collaboration with Thales Alenia Space in order to have a carbon phenolic ablator able to bear with the re-entry condition from Moon. Okay, it was tested at 2.5 megawatt on square meter, and it was quite good success. Obviously, when I test a material in this condition, I say it was tested at 2.5 megawatt on square meter. Okay, but the intensity of the heat flux can depend also on the shape of my material. Okay, so for example, this is the intensity of the heat flux from the center of the material to this point. So you have to consider this line, the center of the material, this point, this angular point, okay, and then this one. okay? And this graph represents the trend of the heat flux along the profile of my material, okay? This is very important for the evaluation, and this is very important also because the heat flux is an input parameter for my finite element model, okay? And so I have to know the intensity of the heat flux in each point of the profile of my material if I want to rebuild the test in the plasma wind tunnel, which is always a starting point in order to have a reliable finite element model for an ablative material. Okay. In here we reported all the test conditions for this material. Some of them are only some characteristics of the plasma wind tunnel. Other one are important characteristics that were used as parameters also on the finite element software. Okay, and this is the video of the test. You can observe that we have this probe which go into position during this procedure. Obviously, the heat flux of the nozzle is yet stabilized. Okay, so the flux is constant. Then, after this condition, the probe could enter inside the heat flux, and it remains inside the heat flux for the time established at the beginning. Obviously, we cannot see exactly what happened to the material because the high temperature. Okay, but we can observe this streamline. Okay. This is the end of the test. Obviously, after the testing time, we had always a period of cooling of the material. And then, at the end, we can observe our material. You can see that this is the shape and the color of the material before testing. And then we have a different shape and color after testing, obviously because we had the phenomena of pyrolysis, and for this reason we had a different material with a higher amount of carbon inside percentage, because only the pyrolysis gas of the phenolic resin were to of the material, and so we do not have phenolic resin. We do not have more phenolic resin on the outer layer of the material. Okay. With this tool, we evaluated also the temperature on the surface of the material and on the bottom of the material. Usually there is some pyrometer which were able to evaluate the temperature on the surface of the material, and then some key thermocouples which are able to detect temperature until 1300 degrees. So they were the optimum choice for this kind of application. And what we can see is that also the shape of the material is a bit changed because of the consumption of the material. And in this case, we have also a good shape of the materials because we can observe that no spallation of the material happened. What is a spallation? Spallation is a phenomenon of rupture of the material very concentrated in a point. So we do not have piece of materials which go away from the material, and so we have not cracks or holes inside the material, and this is very, very important. And this is also this can happen also only when the material is quite homogeneous. Okay, the homogeneity of the material is very important, is not sufficient, but it is a condition necessary for not having a spallation of the material in particular point, but an homogeneous recession, surface recession of the material. Okay.
Excuse me, I have a question.
Yes.
The horizontal lines that we can see in the body is due to the fabrication technique?
Yes, it's due to the fabrication technique because we used carbon felt, which was manufactured in layer. There are several layers put together with a carbonaceous binder. And so for this reason, we can observe these lines. In here, after the charred state of the material, they are more evident, but you can observe also in here, for example. In this image, you can observe all these lines because we have more layer of carbon felt put together. Oh, it's okay?
Okay.
Okay. So, one innovation can be possible for this kind of carbon phenolic ablative material is to introduce some nanofillers inside of them. Nanofillers are very interesting for ablative materials because I can introduce a very small amount of nanofiller and I can have some good results. The importance to introduce a small amount of nanofillers is because I do not want to increase the density of my material. Okay. And I know that with Professor Valente, you spoke about nanomaterials and also nanocomposite. So I will not speak a lot about this topic, also if it's a very important topic for me because I work with the nanocomposite, or with the ablative material and nanocomposites. So it's my main topic of research. And nanofillers are very interesting. The purpose of put some nanofiller inside an ablative material could be for reduce the recession, for example, of the exposed surface. And so we speak about mechanical reinforcing of produced by the introduction of the nanofiller. Okay. Then we can have we can have also a physical stabilization of the char. We can have also a chemical stabilization. This means that we can have some modification, for example, in the thermochemical behavior of this material and of these materials. And in fact, we observed that thanks to the introduction of nanofiller inside the material, the thermogravitometric analysis could be different because nanofillers can influence also, for example, the position of the chains, of the polymeric chains. Okay, and so, for example, thanks to this behavior, we can have higher activation energy for ablative material with the introduction of nanofillers. Okay, so this could be very, very interesting. There are different kinds of nanofillers which can be used for ablative materials. For example, carbon nanotubes were used in order to have a mechanical stabilization of the charge. Okay. Also nanoclay were very used. If you remember, nanoclays are 2D particles, nanoparticles, okay, which are able to give also mechanical reinforcing to polymers because they are able to entangle the chains, and this is very important for the mechanical properties, but also for the chemical properties of these materials. And another choice are the ceramic nanoparticles. Ceramic nanoparticles are important because obviously they bring with them all the characteristics of the ceramic, so low density, low thermal conductivity. Okay. In here, sorry, because for example, in here I will show to you two different tests that we performed in the DLR. DLR is the plasma wind tunnel in the plasma wind tunnel facility of the DLR, the German Research Center for Aerospace. And in this case, we manufactured another kind of carbon phenolic ablator with a lower density compared with the one we saw previously, 300 kilograms on cubic meter. And we tried to test this material at two different heating plugs. We observed this phenomenon. Okay. Okay. This is the test at 6 megawatt on square meter. Okay. We il punto di prima. Scusate. Okay, this is the sample before and after testing. Okay. The recession was quite homogeneous. Then we performed the test at higher heating flux. And I know that the image is not so, the video is not so clear. Okay. You can observe in here that there is a failure. There is a failure not of the material, but of the metallic flange was used to position the material in the right position. Okay. So in this case, at the end, we have this situation. This material was manufactured without nanofiller. It is only a carbon felt with phenolic resin. Okay. So we understood that if you want to increase the performance of our material, we have to do something different. And in fact, we worked on the addition of ceramic nanoparticles to our ablative material. In particular, at the beginning, we worked with zirconia nanoparticles. As a first step, when you have to use something new in a material, you have to understand what can be the effect, for example, on the matrix. Okay, so as a first step, we elaborate a method to optimize the dispersion of the nanoparticles inside some sample of phenolic resin. You can observe in here a sample of only phenolic resin, okay, so this is not the ablative material, but only the phenolic resin. And in here you can observe the same sample of phenolic resin, but with the addition of nanoparticles. In here, 5% of nanoparticles. It means that I have an increment of 5% of weight due to the addition of these nanoparticles. Obviously, nanoparticles are not easy to manage. Okay, if I want to have a good dispersion and distribution of nanoparticles, I have to work, for example, with the ultrasonication dispersion, okay, which is important because they give to the particles an energy which guarantee this dispersion because there is a strong attraction because nanoparticles, because they have a lot of surface and so they are very active. The first thing that we do, so it was not only an observation of the sample that we obtained in this way, but also some mechanical testing. This mechanical testing were not aimed to understand the behavior in the ablative material, but they helped us to understand if we can improve something or the contrary, or if nanoparticles can decrease the performance of our material. But for example, in this case, we observed an increase of the mechanical performance of the material at the increasing of the content of nanoparticles inside. In this case, we do not go beyond the 5% of nanoparticles inside our material. Obviously, then we will perform other tests at higher percentage of nanoparticles inside. But obviously, we have to remember that when we have these nanoparticles inside the material, we always have a threshold who cannot be a threshold for which if I had more particles, I can have a reduction, a decrease of my performance. Because if I put inside the material a great quantity of nanoparticles, I can have the more simpler the formation of agglomerates. And obviously this is not good for the performance of my material. In this case, we can observe the microstructure of an ablative material obtained with a certain process of curing, okay, in which we obtained a good distribution of the resin inside the carbon felt. You can observe that the resin is distributed as very thin films among the carbon fiber. And then we observed also the distribution of the nanozirconia inside the resin. And so we optimized the method with which we can obtain this good distribution of the nanoparticles, even if we always have some small agglomerate of nanoparticles, which is quite a standard situation when you use nanoparticles. This is only a photo of the 4-point bending test. And this is some other good results with the 5% of nanoparticles. Obviously, in this case, we have these results only with the phenolic resin and nanoparticles. In this case, after we observed that the nanoparticles can be dispersed well inside the phenolic resin, we optimized a manufacturing process also for the complete carbon phenolic ablator, so carbon felt, phenolic resin, and nanoparticles. Then we obtained some samples of this kind. We tested them with the 4-point bending test. And also in this case, we obtained the best results with the 5% of nanoparticles inside the material. Okay, obviously we characterize also the char, not only the virgin material, but also the char, which is very important. In this case, we had compression test. Maybe I have here, okay, a photo of the compression test, okay, just to let you understand how could be performed the compression test. Okay, and then at this point, when we understood that we succeed in manufacturing a quite good carbon ablator with the addition of nanoparticles, we were ready to test these materials with the oxyacetylene flame burner in order to begin to understand the ablative performance of this material. I want to remember you that when we perform an oxyacetylene flame test, we cannot reproduce the condition of air entry, okay? But we can have useful screening for the ablative material we manufactured. And so we can understand if they can be tested in a plasma wind tunnel if they are ready to be tested in a plasma wind tunnel. Okay, for example, in here, one important parameter that we observed after an oxyacetylene flame test is the weight loss. In this case, obviously in percentage. Okay, so we will have different samples. For example, 3 or 5 samples for each kind with non-nanoparticles, 2% of zirconia, 5% in weight of nanozirconia. Okay, we tested them at the same condition, and then we can observe the weight loss. And we observed that the weight loss in samples with nanoparticles is reduced with respect to the other one. In this case, we observed also other samples because we understood that zirconia was a good ceramic zirconia nanoparticles are good for ablative materials, but we tried also to test some other nanoparticles, for example, magnesia and silicon carbide nanoparticles. And in this case, for example, we observed that not always we are able to obtain the good results. And zirconia always give the best performance of these materials. But for example, in this case, when we go to observe the distribution of the nanoparticles inside the material, we can find an answer to our question. In fact, this is the distribution of the magnesia inside. We can observe that there are agglomerate of magnesia, an area in which the magnesia is quite completely absent, even if there are some small particles that could be individuated in these micrographs. Then this is at the same magnification the distribution of the silicon carbide. We have macro agglomerates of silicon carbide, and areas obviously in which we have not silicon carbide. Then this is the distribution of the zirconia. All these micrographs were taken at the same magnification in order to understand the distribution of the nanoparticles. So we can say that obviously also the different nature of the nanoparticles can influence the performance of the material, but we are quite confident that the difference is in the distribution of the nanoparticles. Zirconia is more has a more affinity with the phenolic resin and the solvent that we use with the phenolic resin, and also for this reason it could be best results, even if the distribution of the zirconia could be improved more. Okay. Here only some observation. Okay, the dispersion and distribution of the nanoparticles can influence the properties of the ablative materials. A more homogeneous distribution and dispersion can guarantee a more constant recession of the material during N-oxyacetylene flame exposure, so everything is connected. Agglomerates of nanoparticles can be at defect point with a controlled break of the material, causing worse performances. Okay, so this is the reasons why it's very important to have nano-ablative materials with a good distribution of the nanoparticles. So during here we were able to manufacture other carbon phenolic ablator also with the addition of nanoparticles. For the reason that we observed together, we choose the nano zirconia as the nanofiller, and we produced some samples which were tested this time at the VKI, the Von Karman Institute. Okay, and this time we obtained also some good results. Unfortunately, I do not have video for this test because not work on my PC. But we can observe and comment together some interesting image of samples before and after the test. The test was conducted at 4 megawatt on square meter for a test time of 70 seconds. These parameters are not chosen because we want to compare our ablator with other important carbon ablators of the same kind. In fact, we during the last lesson we saw together the EPICA, the phenolic impregnated carbon ablator manufactured by NASA, which has characteristics very similar to our material, and it was tested at the same heat flux. There are also other carbon phenolic ablator, for example, Asterm, manufactured by Airbus. And there is also another ablator, another carbon phenolic ablator, Zuram, which was manufactured by the Von Karman Institute. Okay, and so we chose also conditions which could be comparable for these other carbon phenolic ablators, because we are very interested in understanding how much we can improve the performance of these other ablators. And this heat flux is comparable also with the heat flux experimented, which could be experimented by a vehicle, a re-entry vehicle from low or high energy orbit. Okay, when I speak about low energy orbits, I speak about, for example, a vehicle who has to perform an atmospheric re-entry from, for example, the International Space Station, and for a high energy orbit, for example, we can consider a vehicle which come back from Moon or from Mars or from some exploration of the universe. Okay. Okay. So these two photographs are referred to the material before the test. Okay. In this case, we have this spherical shape of our material. This was our standard material, and this was our material with zirconia addition. Then at the end of the 70 seconds of exposition to 4 megawatt on square meter, we have these two different photographs. When we tested the standard material, we obtained this shape at the end, so an intense consumption of the material. Okay, the erosion was high. When we tested the same material with the same density, but with the addition of nanoparticles, we can observe that the recession is lower. We have a lower recession when we add nanozirconia particles on our material. And we observed this important phenomenon. When we had nanoparticles inside the material, the nanoparticles are all well distributed inside the material. But during dispersion, we have a phenomenon of coalescence of these nanoparticles, and they tend to distribute in the surface, in the exposed surface of the material. This means that I have an external part which consists of zirconia, of these nanoparticles of zirconia, which coalesced during the test and which protect the material from further recession. Okay, these are some micrographs obtained at the end of the test. Okay, this is a micrograph of the external part of the material in which we have a high concentration of zirconia. And we can observe from the microstructure that we have a coalescence of the nanoparticles. Then we have a micrograph of this part of the material in which we do not have this big agglomeration of nanoparticles. But at the same time, we can observe some phenomenon of coalescence on the carbon fiber. When the phenolic resin go through pyrolysis, and so there is a decomposition phenomenon of the phenolic resin, there is also a coalescence of the nanoparticles. And nanoparticles in this case can protect the fibers from further decomposition. So this is a very interesting phenomenon which could take place when I add nanoparticles to this kind of materials. In literature, we have a lot of research on ablative materials enriched with nanoparticles, even if there aren't ablative materials at an higher development phase with nanoparticles, while our material is at a good point, and also because we can control quite well the distribution of the nanoparticles inside the material. We tried also to improve the distribution of the nanoparticles thanks to some surface modification of the nanoparticles, the functionalization. But I think that you studied this functionalization of nanoparticles when you studied nanocomposite material. And this is only a comparison of different kind of material with our material. Okay, so after is this ablative material designed and manufactured by Airbus. And these are the performance of our material in quite the same condition. So we think that this could be a good result, and this result could be also a good idea because we understood that enriching the carbon phenolic ablator with nanoparticle could be a successful strategy. Okay, and with this last information, I finished my presentation. I don't know if there are some questions about this about ablative materials. If there are questions, I'm here, and if not. Yes. Yes. Sorry? What happened? Yes. Oh, we don't know exactly what happened, but for example, zirconia has a very high melting point. Okay, the material do not reach that high temperature, but we have nanoparticles, so there could be a phenomenon of lowering of the melting point, but the particles are not melt together. There is a coalescence due to the fact that part of the phenolic resin decompose, and so nanozirconia particles goes to a temperature as high to hollow for phenomenon of coalescence. Okay, there is also a very external part of the nanoparticles who can melt. Okay, and so they go together, but we are not sure about the mechanism for which they tend to go together during this phenomenon of partial melting of the nanoparticles. We are studying about this phenomenon, and it's very. Oh, you're welcome. Okay. If there are not other questions, I don't know if we will see again during the course. And thank you for your attention. I hope that this presentation was quite interesting for you. And have a good evening. Goodbye.